Hi, my name is Kelly Pohland. I am a graduate student at the University of Oregon. I study equivariant homotopy theory under the advising of Dan Duggar. And I study a cohomology theory called Bredon cohomology for spaces within action of a group G. It's graded on ROJG, the Grothendieck group of real finite dimensional orthogonal G representations. And specifically, I work in the case G equals C3, so I'm going to be using that a lot. And I want to talk for a second about why we might want to consider a cohomology theory graded on ROJG. So given a representation of C3, we can write it as some number of copies of this one-dimensional trivial representation and some number of copies of this two-dimensional rotational representation given by rotation of the plane 120 degrees about the origin. When we write it in this way, V is completely determined by the values of P and Q, where P is my total topological dimension and Q is the number of copies of this two-dimensional rotational representation. And given such a representation, I can construct a sphere called a representation sphere by one-point compactifying and adding a fixed point at infinity. So looking specifically at this example, I can obtain this sphere by starting with this two-dimensional rotational representation and one-point compactifying and adding a fixed point at infinity. And this gives me a rotating sphere. And okay, I have this class of spheres, and if I have some other C3 space X, I can take the smash product of this sphere with X. And this gives me some notion of suspension for which I have a suspension isomorphism. And this is really where we want to highlight the use of ROJG here, because we need to be able to add representations in our grading in order to make sense of the suspension isomorphism. So this cohomology theory takes coefficients in Mackey functor, but I am working specifically with the constant Z3 Mackey functor. So I'm going to suppress that notation going forward. And I just want us to think of this for the purpose of this presentation as analogous to singular cohomology and Z3 coefficients. And again, another piece of notation here is since V is completely determined by these values of P and Q, I'm going to consider this to be a bi-graded theory, and I will just be grading over P and Q. So my goal of my project was to compute the cohomology in this theory of all surfaces with an action of a cyclic group of order 3. And the first step here is to understand what all these surfaces are, to classify all these surfaces. This classification problem is classical, but I wanted to rederive a classification that was more accessible and more geometric in nature. And I did this using equivariant surgery methods. So I was able to show that the isomorphism type of a closed, connected, non-trivial C3 surface depends only on whether or not it's orientable, the genus of the surface, and the number of fixed points it has. And I was also able to describe the isomorphism classes. So every isomorphism class is represented by some surface obtained by starting with one of 5 basic examples of a C3 surface and then performing some number of these equivariant surgeries on it. So these 5 examples here are shown on this slide. So there are 2 free surfaces, one orientable and one non-orientable. So I have a free action on the torus and a free action on the Klein bottle. And then the other 3 surfaces here are non-free. So these fixed points are shown in blue in these pictures. So I have an action on the torus with 3 fixed points, an action on RP2 with 1 fixed point. And these we can obtain by representing the torus and RP2 using identifications of the hexagon and taking advantage of the C3 structure, or sorry, the order 3 symmetry of a hexagon to induce a C3 action on each of these spaces. And then we have this sphere that we mentioned earlier. So the idea is you start with one of these 5 spaces, and then you can construct more interesting, more complicated surfaces from them using these equivariant surgery methods. So there's only 2 surgery methods I actually need to understand my classification. So I'm going to describe them here. So the equivariant connect sum starts with some C3 surface X. I remove 3 conjugate disks from X, giving me 3 boundary components. And to each of these, I'm going to attach some non-equivariant surface with a disk removed, and I can define a new C3 surface by saying that under the action of C3, each of these copies of, in this example, the torus minus the disk, they all map to each other under the action. And then I also have another surgery called equivariant ribbon surgery. So I've got this special surface with boundary here called R3. It's got 3 boundary components, which I've highlighted in red. And I can take any other C3 surface. I can remove 3 conjugate disks from it, giving me 3 boundary components. And then I can identify the boundaries of these 2 objects using some equivariant map to give me a new C3 surface. For example, this one. So here on this slide, I just have listed the isomorphism class representatives here. And really, I'm just going to highlight again and emphasize the fact that this just says start with one of these 5 surfaces I had a couple slides ago, perform some number of ribbon surgeries on it, and then perform some equivariant connect sum surgery on it. And this gives me a surface. And I'm also working on an analogous statement for CP. It turns out there's a very similar story when you work mod and action of the automorphisms of CP. So once I have the cohomology, once I have the classification of all these surfaces, I wanted to compute their cohomology, and I did this. And I will just highlight that I computed their cohomologies as modules of the cohomology of a point, which I call M3. It turns out that there are only 5 M3 modules here which show up in the cohomology of these surfaces, and the multiplicities of these modules as they show up is completely determined by, again, these same properties of whether or not the surface is orientable, the genus of the surface, and the number of fixed points of the surface. So I just want to give you a picture of what some of these M3 modules will look like, so we have a better idea of what these cohomologies look like. So M3 itself, the cohomology of a point, it's very complicated. So in this picture, again, since we're bigraded, I have drawn the PQ's cohomology above and to the right of the PQ spot on the grid. So we've got these generators X, Y, and Z shown here. Those are all generating copies of Z mod 3. And the top cone here is isomorphic to polynomials in X, Y, and Z, where Y squared is 0. And then I've got this element W in the bottom cone, which is infinitely divisible by X and Z, and it's divisible by Y. So this thing is already really complicated for the cohomology of a point. So these computations are not particularly easy. And I am going to just abbreviate this picture by just outlining the cone, because there's a lot of information there, and to make these computations easier to understand, I'm going to drop some of this notation, but we do have to remember that there's a lot of structure hidden here. So some other M3 modules, so the cohomology of C3 is another M3 module, just a tower of Z3s. This guy here is the cohomology of the circle, which freely rotates 120 degrees. And then the last one that I want to highlight here is the cohomology of this space called the egg beater, which I'm denoting EB. And I can define this to be the cofiber of this map, which sends C3 to a fixed point. So that's depicted here. And its cohomology is shown here on the right, again, using the same conventions as I had for the cohomology of a point. So I have an abbreviated picture for this one as well. And I just wanted to show you in a typical example of what a cohomology of one of these spaces might look like. So I've got this C3 surface here, which I built by starting with this torus from the hexagon picture. I've performed C3 ribbon surgery on it. And then when I compute its cohomology, I get, again, some summand of these M3 modules. In this particular case, I get a copy of M3, a shifted copy of the cohomology of a point, and then I see a few of these egg beater cohomologies showing up. And these multiplicities, again, are determined by genus, number of fixed points, things like that. So from here, I really want to do some computations in some other coefficients. Not all of these different isomorphism classes are distinguished using this cohomology theory, and I want to try to see that. And also, I want from here to work on computing the cohomology, the ROCP graded cohomology of CP surfaces. Now that I have this, I'm working on this classification of CP surfaces when P is greater than 3. Thank you very much.